The function to a state space representative or canonical form. This figure that we saw together, we have a discrete equations with the z transform. You can find the transfer function. In the inverse z transform, you can come back from the transfer function to the difference equations. We saw how you change the state space model to the transfer function and vice versa. Now we want to see some properties of the state space representative. Canonical form of the state space equations, you can write the differential equation of the numerator and the denominator. A state space representation of the system is not unique, but some canonical forms are controllable, observable, diagonal, and the Jordan forms are unique, and is very helpful for us. Just I would like to talk about the controllable and observable that you saw a lot and you will see in the future. If you have a plant in your system, then you have the actuator here. I can write the actuator, and you have the sensor. The total plant will be included both the actuator, the plant, and the sensor. This is the total plant. But actuator, you need the import control force and energy for here, because this is here is a controller. The controller, they give the force to actuator, and actuator they work for the plant. Sensor is a measured state and the output of the system. Controllable, or the name is reachable, you need to be able to influence the system. You need to influence the system by the actuator. Knowing all of the state variable, you need a sensor. The name is an observable sensor. And I can say the control signal which allow the system to reach any state in the finite amount of the time, the name is a controllable. And all state can known from the system is come from the sensor is observable. We can give the example. What's the meaning of the controllable? If you have a car, the car, they show you they have two states in the car. Imagine you have one of them is a velocity, one of them I can write the x1 and x2. One of them is velocity, one of them is position. And here is a velocity. If you can measure both of them in any state of here, your system become observable. Any of them you can reach is a controllable. For example, I want to reach to this velocity and these positions. If I can reach to these things, my system is controllable. If I can know about the both of this position and the velocity, the system is observable. This one we discuss more, just only I give you some definition about the observable and the controllable. If a matrix A becomes such as, if you remember the canonical form of the system is a B0, B1 until Bn, and the denominator start from here is a 1, A1 and An. If the matrix A change such as this matrix A, all here becomes 0, the rest at the top become 1, and the last row of the system become start by minus a1 until minus an. That means this one in the denominator of the signals. The output, you have the one input. The output will be started by the bn minus an b0, bn minus n minus an minus 1 b0, etc. And the b0 become the multiplied by the input. This system, the name is a controllable canonical form. Example, consider the following system here. Give the state represented in the control canonical form. If you remember the canonical form, standard canonical form here, b0, etc., you can understand that this one is a b0, and this one become, for example, b1. Here z2 is here become a, I don't know, I put a1 or a1, and here become, for example, a n or a2. Then if you put in the matrix that you saw, b0 is 0, b1 is 1, and b2 is 1, and a1 is 1 point, a2 is 0.4. If you put in the matrix, this system is controllable. That means if you imagine you have a two variable x1, x2, because the matrix A is a 2 by 2, you have a two variable, you can reach both of the variable because the system is controllable, because I made such as the matrix A become this, matrix of the C become this, and matrix of the B is here. Observable canonical form, the matrix of the A, the last row of the controllable become the last column of the observable. The matrix of the in the output of the controllable become the input of the observable, and the input of the controllable become the output of the observable, and here is the same. If you see, for example, consider the following system, give the state a space representation in the observable canonical form. I want to change the transfer function to become my system observable. Why observable? That I can know all of the state variable of the system. Just it's easy. You find the b0, b1, b2, a1, and a2 from the transfer function. You put in the matrix, then this one become the an minus bn, the same as the matrix that you saw the previous slide, and here become the output. This system or this model is observable for me. Observable, that means I know in each time I can measure the each state variable. You have a two state variable x1 and x2, and each time you can know about the variable. Diagonal canonical form, if the pole p1 until pn of the transfer functions are all distinct, may be complex, then the diagonal canonical form will be something like this. That means if you see the transfer function here, after the partial fraction, you can find the p1, p2, pn, and the denominator becomes c1, c2, cn. Diagonal canonical form, the pole will be in a diagonal, and the output become the numerator about the transfer functions, and here become 1, 1, 1, 1, all become 1. Okay, this is the system. Give the state space representative in the diagonal canonical form, and easily you can find the, based on the partial friction, you have the two pole, and here become the denominator. The two pole become in the diagonal form of the system, and the output become the denominator of the transfer functions. The last canonical form then is the Jordan canonical form. If the pole P1 is a multiple pole of the order m, that means the pole is repeating. The transfer function, all of the other poles are disconnected. Then the Jordan canonical form will be P1, P2. This is the system, and here is a repeating of the pole. The output become the denominator of the transfer function. With one example, we solve this problem. Here, two pole in the z equal to 2 is repeated, and you have one pole is minus 1. Canonical form will be two pole P1, and another one is a P' one that's repeating, another pole is become the diagonal. The output become the denominator of the transfer functions. Non-unique of the state space representative. Definition of the new state vector, I can say the, for example, xk become one matrix multiplied by the x hat k. I can define the new state vector for xk p x hat k, where the p is a non-singular matrix. What is the state space representing using the x hat k as a state vector? You have a state space. I want to define the new state vector x hat k with the matrix about the p. Now I want to see what is the state space representation using the x hat, that means the state, new state vector of the system. Okay, I know the xk plus 1, this is the state space, become g xk plus h uak. I substitute the xk is p x hat k, that means here become p x hat k plus 1 is equal to j p x hat k plus h u k. If both sides multiplied by p minus 1, this p minus 1 where p become 1 become x hat k plus 1, p minus 1 g p become x hat k plus p minus 1 h u k. If I define the p minus 1 gp, that means p inverse gp, I put a g hat, p minus 1 h, I put a h hat, then I can say the x hat k plus 1 become g hat k, g hat x k plus h hat k u k. This one here is wrong, this one become y k become c xk plus d uak. Okay, I found it. One example, consider the following system you have. State space representative. Find the state space representative of the above system using the state vector. That means they give me the p here. They want to ask me to find the xk plus 1 hat is equal to become p minus 1 g p x hat k plus p minus 1 h u k. I know about this is the g, this is the h, I know the p, I find the inverse, multiply together, I will find the x hat k plus 1. Okay, this is the new vector we define for the state space representative, solving the discrete time state space representative.